Officially, osmolarity refers to the number of osmoles of solute per kilogram of solvent. Yeah, that means very little to me. So it measures how many particles of solute are present in a given mass of solvent. Imagine you're preparing fruit punch and you are interested in how many fruit pieces, and that's your solute, are present in each liter of the punch. That's your solution. And can I just say, this sounds more like sangria than fruit punch? You are focusing on how many fruit pieces are present per kilogram of just the juice, and you're ignoring the volume added by the fruit itself. In clinical practice, osmolarity is often preferred because it's measured based on the mass of the solvent, and that makes it less susceptible to changes in temperature and pressure. I think it was Charles's law, right? Says that things expand with temperature. But osmolarity provides a more accurate assessment of a solution's concentration, especially when there are physiological conditions happening. Osmolarity, being volume based, can be influenced by environmental factors that affect volume, such as temperature fluctuations. But in general, if your osmolarity is high, you are dehydrated despite how much blood is in your body. If your osmolarity is low, you are well watered despite how much volume of blood is in your body. I could house everything in this picture, like all of it. Are those bugles over there on the right? Have you ever read a nutritional label for bugles? They are so bad for you. All right, think of yourself eating a round of these really salty foods. You've put more solute in your blood, right? And you didn't drink anything. So you've increased the osmolarity of your plasma. Although you've not changed the water content of your body, you have changed the solute content, and thus you've changed your osmolarity. You've raised it. There's another way that you could raise your osmolarity. Even if you don't eat salty foods putting excess solute in, you could urinate out some very dilute urine. As you do that under the influence of ADH or a diuretic. By doing that, you're reducing the solvent and you've increased your osmolarity. So let's talk about beer and pretzels for a moment. First of all, alcohol turns off ADH, and that makes you pee very diluted urine, raising your osmolarity. If you eat the nasty bowl of pretzels on the bar, you are giving your plasma a double punch of increasing the solutes with the salty foods and decreasing your solvent with turning off ADH. And this is why salty foods and alcohol are like a double punch for increasing your plasma osmolarity. When the body experiences dehydration, the first area affected is the extracellular fluid, which includes the plasma and the interstitial fluid. Water can be lost through sweat, respiration, urine, or even vomiting and diarrhea, leading to a decrease in the ECF volume. So, as a result, the osmolarity of the ECF increases. And that's what we see right there. This means in the ECF there are now more solutes like sodium relative to the amount of water, and the osmolarity has increased. Because water moves by osmosis, it flows from areas of low solute to high solute concentration, and in response to this very hypertonic ECF, water is drawn out of the cells and is put into the ECF. This helps restore the ECF volume, but only temporarily, because it comes at a cost. The cells that you're drawing the water from, those cells shrink, and form equals function, so cellular function becomes impaired, especially in sensitive tissues like the brain. To compensate all of this, the body achieves or it activates hormonal mechanisms. Antidiuretic hormone is really the one combating force here. It's released to increase water reabsorption in the kidneys and produce very concentrated urine. It also stimulates thirst, and this prompts a person to drink water over time, restoring the fluid intake, shifting the fluid back into the ICF, and retaining the water that helps create isotonicity in these fluid compartments. Thirst can lower your ECF osmolarity, but it also raises your blood volume. And we've avoided blood volume as a factor for osmolarity, but there are consequences, definitely, for having too much fluid volume in general. So you drink some water to lower that osmolarity, and immediately the kidney stops reabsorbing or keeping so much sodium. More sodium is lost in the urine, and that decreases your blood's osmolarity, but it increases the osmolarity of your urine. And this means that your urine is going to be more concentrated, it's going to have more solute in it, and this would increase the color as well as the specific gravity. Recall that we said your body manages the sodium concentration among your fluid compartments in order to maintain the osmolarity of extracellular fluids. So if your osmolarity is high, you could always drink water to decrease it. However, thirst is not so simple. It's an emotion, much as hunger is an emotion. And people can avoid and ignore the plea of thirst from their body. Thirst is triggered easily by having low blood volume or low saliva. Baroreceptors in the aorta and carotid artery are also capable of sensing when blood volume is low. There are osmoreceptors in the hypothalamus that are monitoring the plasma osmolarity. If it goes too high, or if your blood gets too salty, thirst will be stimulated along with the hormone ADH. The easiest way to raise your blood volume is to add water by drinking it. Thirst does that if you respond to it. Also, by drinking the water, you are adding solvent without adding solute. And this waters you down, decreasing your plasma osmolarity and hopefully returning it to where it wants to be. Hypotonic hydration is also called water intoxication, and it occurs when excess water is ingested or retained, and that dilutes body fluids, lowering your plasma osmolarity. This creates an osmotic imbalance between the ECF, including plasma and IF, and the intracellular fluid compartments. Since the ECF becomes very hypotonic compared to the ICF, water moves down its concentration gradient and it moves into your cells, causing them to swell. In terms of fluid compartments, the interstitial fluid becomes more dilute first, as it's part of the ECF, but its reduction in osmolarity causes water to shift into the cells, and that expands the intracellular fluid volume. So cells in most tissues can tolerate the swelling to some degree, but brain cells are especially sensitive to this. The swelling of neurons can lead to increased intracranial pressure and result in things like confusion, nausea, seizures, and even coma in very severe cases. Hypotonic hydration is a shift of water from the IF to the ICF. And therefore, the only way to really fix it is to add salt to the extracellular fluids and draw the excess fluid out of your cells. How can we do that? Just a Ringer solution of an IV.